the morning session. Welcome everybody, and we start with Masahito Yamazaki, and he's going to tell us about the Theta Vacua in 40 years.
Okay, can everybody hear me, I guess? Okay, so first of all, let me thank the organizers as other speakers for kind invitation. And in fact, I was kind of, I wasn't sure until the last minute whether I could make it. So I'm very happy that I'm here in Ascona. And well, so today I'm going to talk about Theta Vacua in four-dimensional Yang-Mills series. And this is work in collaboration with Yuichiro Kitano, Ryutaro Matsudo, Norikazu Yamada, located at KEK. If you don't know what KEK is, it's where the collider is, where, for example, Beta 2 experiment is going on, and there is a theory group there. And my talk is about the two papers which I put out last year and this year. But the difference from other talk is that it's actually in Hep lattice. So hopefully I'm not going to lose you, but so some of the what I'm going to talk about is the 4D Yang-Mills theory. In fact, it's a pure Yang-Mills theory and no supersymmetry, no matter. But you can certainly think about adding matter, etc. But at least my talk today is about the pure Yang-Mills, and the gauge group is SU2, the simplest case. There is similar story for SU3, etc. But there is some particular reason why I'm interested in SU2, as I'm going to explain later. And then include a theta angle, which is the coefficient of FF tilde, as everybody knows. And the question itself is extremely simple. So the question is that there is a free energy per volume, which is defined here, and it's a simple function. And I want to know how does this looks like as a function of theta angle theta. So it's a very simple question, and I'm sure that this question has been around for since the invention of the theta angle, almost like 50 years or so. And but surprisingly, there are still some questions to be fundamental questions to be understood about this. And one of these is indeed what happens at the theta equal pi. So what's special about theta equal pi is that there is a CP symmetry. So theta goes CP sends theta to minus theta, pi goes to minus pi, but theta is periodic, so it comes back to pi. And that's another point apart from theta equal to 0, where there is a classical CP symmetry. And there's a big question: what happens to that CP symmetry afterwards if you take the order dynamical effects into account? And as we explained, this is very much related to the question of whether things confine or not. So whether there's a gap in the spectrum or gapless or not. So that's a big question in the field. Now, certainly this has been, the question has been around for a long, long time. And there are important insights, which I'm going to review, although there are actually not too much progress in this respect, but there are some. And one of them is the instantons. Of course, that's in the textbook computations, but the Hooft and others. And so why don't you do the weak coupling computation, the instantons? And in the end, the one instanton contribution gives this cosine term. And there are also two instantons, etc. But you might expect one instant dominates. And whatever the structure is, the crucial structure here is that it's 2 pi period, which is of course natural because the theta angle is 2 pi period. So so the potential looks like this. Okay, I'm not good at writing the cosine function, and maybe there's a cosine to sigma, etc. It's a little bit deviation, but anyway, it's a 2 pi period. And so this is the what people call the discrete instanton gas approximation, so instanton approximation. And it actually works when the theory deconfines above the critical temperature. But as I'm going to show in the next slide, people already know in the 80s or so that this is not actually a correct answer, at least when t equals to 0 and pure Yang-Mills. This is not the correct answer. In fact, there's a lot of confusions in literature. If you open the Coleman's lecture, for example, he says, oh, okay, there's a divergence. But subtle is that there's a divergence in this integral when log goes to infinity. It's IR divergence. And Coleman says that, okay, so let's regularize, but it's fine. But actually, it's not the correct answer in general. And the argument was provided, well, not too surprisingly, by Witten, and in the 80s or so, using the large n. And the argument itself is actually rather elementary. So, okay, so this is the Lagrangian for the Yang-Mills theory, but written in a little bit funny way, where there's a 1 over n. So this is the h bar parameter, expansion parameter. And then, of course, then you have to extract the power of n. And in particular, the theta appears in combination with n as a theta over n. Okay, so this is a simple scaling argument. And now, of course, the assumption is that the set large n limit makes sense, keeping this as a parameter. And we know that the degrees of freedom of the Yamu series goes like n squared because it's matrices. So I changed the notation. Sorry, f of theta, the free energy, scales like n squared times this combination. And then, well, there's a CP symmetry. You expect, so there is a theta goes to minus theta. There is a symmetry of sending theta to minus theta, at least you expect. And then it's a quadratic expansion around theta equals 0. But if you like, there is a abstract, but not abstract. There is a good argument by Vacua and Witten in the old days that theta equals 0 is a minimum. So indeed, there's a quadratic things happening. And then there's all the high order corrections. And from this large n argument, you can extract the large n dependence of this coefficient, which is noted chi, and also the subreading coefficients, which I take to be dimensionless, B2, B4, etc. That's the convention in the literature. And this chi goes like a constant in the large n limit, and B coefficients, they become smaller and smaller in the large n limit. So that's the prediction from large n scaling. It's a very simple scaling argument. But surprisingly, this is extremely powerful because, so you see this coefficient goes like 0. So in the strict large n limit, the only thing remains is actually just the quadratic potential. And but the point is that quadratic potential is not 2π periodic. And so another way of saying that is that there are actually multiple branches of cosine functions as quadratic functions. They are quadratic functions. There are many quadratic functions of order n. So in general, you are in a metastable branch kind of. And the true vacuum, if you want the true vacuum, you have to take the this absolute minimum among all the branches. And then the crucial point here is that the 2π period is lost. If you look at one of the branches, and recovered only when you look at the if you take the minima among all these branches. So physics itself, in a sense, is a 2π periodic still, but there are metastable branches. So that's the simplest argument by Witten in the large n limit. And what's particular, this implies in particular is that if you look at theta equal pi, it's a little bit small in this picture, but the theta equal pi is the point where, not theta equal pi, this is not theta equal pi. Sorry, I messed it up. But but the theta equal pi, so this is theta pi over n. But what's peculiar about this is that there are multiple branches coming up. And so in general, that's the point where the two branches meet together. So if you move away from one value smaller than pi to the other side, etc., you have to transition from one branch to the other. So that's where the CP symmetry breaking happens. And yes.
Sorry, it's just a simple question. So why do you have another minima at 2π over n and 4π over n? I didn't understand.
Oh, sorry. Yeah, in fact, sorry. Yeah, in fact, I think I got it. I got this wrong. So this should be 2π. Sorry. Yeah, sorry. Yeah, that's a mistake. So this should be 2π. This should be 4π. Yes. So the only thing that happens is that there's a quadratic potential, and because there should be theta minus 2π squared, there should be another branch. Yes. So this is 2π, 4π. Yes, that's a typo. Sorry. And so this is the point where theta equal pi, where two branches meet. That's where the CP symmetry is broken. Yes. So this is a scaling argument. I hope everybody gets it. And so it's hard to fight against this, at least in the large n limit. Now the question is that large n limit is beautiful, but there is often a question that I'm interested in SU5 theory, for example. Does the large n argument apply? Well, strictly not. If you're serious, you might say strictly not, but sometimes large n limit do apply. And then, so you might begin to wonder, so in the large n limit, CP is broken, spontaneously broken, but then what happens in general? Well, so theta equals to pi, and then you try to change the value. So this axis is like a large n, and so in the large n limit, so this is actually 1 over n, sorry. It's 1 over n. In the large n limit, so that's where close to here, so n is close to infinity here. And that's the region where CP is spontaneously broken. That's what I said so far. So this axis is 1 over n. And so here is CP is spontaneously broken. But now there is an argument using mixed anomaly, which says that there is a mixed anomaly between CP and center symmetry. Which means that at least one of the CP or center symmetry should be broken. Well, of course, both can be broken. So they can be, this itself doesn't exactly tell you what exactly the phase diagram is. So because both might be broken and there might be multiple regions, phase transition, etc. But for this argument, for this talk, let's assume that there is a simplest structure you can think of. Namely, either the CP is broken or the center symmetry is broken. So let's assume that's the case. And here, okay, so the CP is broken. But you actually expect that as the value of n becomes small, so 1 over n becomes large, there is some critical value above which, let's see, the CP becomes unbroken. And in this case, the center symmetry should be broken. So it becomes gapless. So there's a mixed anomaly. So there are two possibilities. As a minimal choice, you expect a phase transition. And this is a function. Okay, so this axis is n length of the amino theory, which is of course the integer. So it's 1 over integer in this case. But you can try to analytically continue, and you expect that there should be some transition point in between. And the question is that what is the value of this n critical NCP? Is it 1 over 2, 1 over 3, etc.? And depending on that value, you might expect the interesting structure, especially when n is small for SUN. And of course, the most extreme case is SU2. SU2 is the case where n is the smallest, farthest away from a Largian limit. And the question is that, is SU2 theory, for the SU2 theory, is it here on this left-hand side of this, namely CP is broken, or is it on the right-hand side, is the CP is unbroken? So that's the question. And this question itself is actually natural. If you take into account the comparison or analogy with a 2D CPN minus 1 model. So 2D CPN minus 1 model, there is this SUN global symmetry. So it's actually useful to compare with the 2D CPN minus 1 model with SUN. And there, people believe that to know the phase diagram, and then there is indeed something very special happens at SU CP2 minus 1, CP1, and at the theta equal pi, and that's the related with the Haldane conjecture, etc. So people believe that among all the CPN minus 1 at theta equal pi, CP1 is very special because that's where the CP is unbroken and there is a gapless spectrum. But all others are CP is broken and gap. So it's like a large n. So in a sense, I would say that roughly speaking, that it's n equals 3 is large and n equals 2 is small in this criteria. And the question is that what happens is, so if you people take this as an analogy, for example, so if you take that face value, n equal 2 should be small in that criteria, even for the amuse. But is that the case? And of course, this is just an analogy. But if you want to go beyond analogies, there is actually more precise connection, which I developed with Kazuyo Yonekura some time ago. So you can start with 4D SEN super amuse, compactify on S1 times T2, include the Tofuft magnetic flux, etc. And then you get some signal models whose topology is like a CPN minus 1. So there is some connection. And you can even try to match that there is a mixed anomaly here, and there is a mixed anomaly here, which I matched by dimensional reduction, etc. So there is a more precise connection. But nevertheless, that connection requires a lot of extrapolation from one radius to other, etc. So it doesn't guarantee that there is a quantitative comparisons between these two are legitimate. So there's a big question whether SU2 is SU2 and n equal 2 is small or large. So that's the question I'm going to address. And I have been interested in this question for a long time, but I must say that it's extremely hard to address this question, simply because there are very few tools, surprisingly. And that's why I started thinking about doing the computations in the numerical lattice simulations. At least there is a way to compute things, which of course has been a challenge for me because I'm not educated in lattice, at least traditionally. But at least you can do it. And then there are a couple of subtleties, but there are many subtleties. But here I listed only two. The one subtlety is related to the question of how you measure the topological charge. Okay, so I want to know the dependence of the free energy as a function of theta, and the conjugate variable is the topological charge. So I want to know the topological charge, which is the integer. Now, okay, so the first thing you might think is that, okay, just discretize everything, and discretize is the definition of FF filter, and you get something. But actually, that's not good in the sense, okay, you can get some quantity, but actually not that good because it's not quantized, first of all. And so if you have a smooth compilation of gauge field compilations, mathematical theorem tells you that it's quantized, of course. But on the lattice, it's not guaranteed. So, for example, it might widely fluctuate. It might converge into a non-differentiable function, etc. In the limit if you try to take the scaling limit. So all these things are included when you do the lattice compilation because there is no notion of continuity between different points. It can be 1 and -1 at the neighboring point, but they should supposed to converge. So That's well known. And for example, Russia has been studying that and then try to get away this dangerous configuration by imposing admissibility in condition, etc. But anyway, so that's the question of how to define Q itself is a non-trivial thing. And there are certainly people have, yeah, I didn't list all the references, but lattice experts have thought about that. And basically the idea is to smear things. So it's widely fluctuating. So if that's the case, you introduce some smearing procedure to make it reasonably smooth. And after that smearing procedure, you define the topological charge. And I'm going to show you a little bit more data points afterwards. Now, what is the second ingredient? The second difficulty, this is the extremely hard one, the sign problem. And this is a well-known problem in numerical computations in Monte Carlo, etc. So the action we want to do is the gauge field action together with the I theta q. And there is a factor of I, imaginary I in the Euclidean signature. And so this is widely fluctuating. And in fact, theta equal pi, precisely the point I want to identify, is the worst point, because theta q is an integer. So exponential I pi is -1. So there is a plus, minus, they contribute, and they cancel each other. So that causes a numerical problem, and that is a sign problem. So that problem is still there. I don't think I can solve it. And so if you want to proceed, you have to find a way to kind of circumnavigate it one way or another. And a lot of people tried various things. For example, people try to analytically continue the value of theta to pure imaginary theta, and they try to extrapolate back to theta, real theta. And which is great, except that then you have to do a large extrapolation, because you have to start with the I pi, for example, all the way to pi, which is not that close. So you have so you can try to extrapolate. Sometimes it works, but you have to know the functional form in a sense to ansatz to extrapolate all the way to theta equal pi, which is non-trivial. If you don't know the functional form, and what I want to do here is I want to know the functional form of the free energy as a function of theta. So we started doing things. The first thing is actually what a lot of people have done already in other series. One is to try to expand around theta equal to 0, just the small fluctuations. And then if you do the Taylor expansion, and then free energy can be expanded in this form, theta squared, theta fourth, etc. So this is the same expansion as I've shown before. And then I try to compute these coefficients. And that you can do without any problem, because you can use the same gauge computation theta equal to 0. Now, the next ingredient, which is actually the newest part of our method, is to introduce something else, which I call the subvolume method. And that's what I'm going to explain. And in this method, you can actually plot the f theta as a function of theta. But I'll explain it later. Hopefully I have enough time. Okay, so let's see. So let's first do the expansion around theta equal to 0. And there are certainly a lot of papers, especially many papers, especially the paper by Massimo D'Elia and others, like that, I think group of Pisa. And so, okay, so the first thing, first thing is to expand around theta equal to 0. This is actually conceptually simple. Okay, so you generate the gauge configuration at theta equal to 0. Not a problem. You can use the standard program. You don't have to modify the program. And then measure the topological charge. And there's coefficients, topological susceptibility, B2, B4, etc. There is already a formula. So you just measure the Q and then just measure the this expectation value of Q squared, Q to the fourth, etc. And you can measure these coefficients. And in fact, I was somehow interested in these coefficients for a completely different reason. I was once working on models of axionic inflation, which we call the pure natural inflation, which seems to be fitting well with recent constraints on tensor scalar ratio, etc. And for some of the analysis, whether we're going to detect gravitational waves, etc., the precise value of these coefficients was important. So that's actually how I became interested in this. So I just mentioned it just in case that there is some completely independent interest in these coefficients. But anyway, these are some coefficients, and you can compute these coefficients. Try to compute you are using this formula. So that's conceptually very simple. The hard part is that, okay, so this if you want to compute these coefficients, you need to show the deviation from Gaussians. You have to fight with the Gaussians. In fact, this is the topological charge. First of all, this is how we measure the topological charge. So you just generate the gauge field configuration. It looks like this. It's not at all quantized. And then we apply some smearing procedure. So this after 20 steps or so, it becomes this green, and after 100 steps, it becomes this, which is highly peaked along integer points. And this certainly is known for a long time. And what type of smearing procedure we use, there are various ingenious techniques come up. Theoretically, most satisfying one is the gradient flow by Lucier. And the one we used in particular in practice, which is a little bit faster than gradient flow, is called APE smearing. And APE smearing APE stands for Advanced Processing Emulator or something like that. It's the name of supercomputer. And it happens that it was built in the 1980s at Rome and also at CERN. And the group of Rome, partly led by, I think, by Parisi. So congratulations to him. And so it's amazing that people have come up with some smearing procedure. And so after the smearing procedure, this noisy thing kind of goes away, and it converges quickly to integer values. Well, of course, there you can discuss systematics, starting with how this procedure, etc. And but except that, so sometimes people just do this procedure after say 50 steps, and then just do the computations there. But we actually improved a little bit on this procedure as well. So because then I had a question like, okay, so if it's fine to do 50 steps, and then but then how do you decide whether you do 50 steps or 100 steps or 100, 300 steps, etc., which wasn't completely clear to me. And indeed, it actually matters. You want to get the precise predictions. So this is an example of the topological charge, and I keep doing the smearing procedure. So this is 50 smearing steps, 100 smearing steps, etc. And then there's this red and blue, etc. These are the points where topological charge are concentrated. So, okay, this is a little bit of a cartoon. Of course, if the whole actual thing is in 4 dimensions, 4 space-time dimensions. So, but anyway, there's a cartoon, and then you can see that after so you start from here, do the smear step to the right, down, right, etc. And then you see some of these charge, Instanton charges concentrated, kind of getting smeared away. And after 500 steps or so, it's kind of gone, at least to the human eye. So it actually it matters how many steps you do. So we improved this procedure by first, okay, there's some smearing procedure up to some point. It kind of goes away quickly. But then after some point, there is a gradual decrease of the topological charge. So we propose a method to extrapolate back to say the 0 step of smearing step by finding a fit function, which in practice is linear function all the way, etc. So there are a lot of subtleties as to how to define the topological charge. But you can do it, and the end result which our first paper is the follows. So this chi and B2, so these are the coefficients of the theta squared and theta to the 4th term, and so we took the continual limit. Unfortunately, as I said, this you have to fight with the Gaussians, and I had to take 2 years to generate the gauge field configurations, and so already partly because I don't have that much computational resources. But then at least we did some analysis, and indeed we obtained some constraints on this value of B2, which is non-zero, at least in the 1 sigma. Okay, so we get some value, but what does this tell us about the physics? There is a physics you can extract already from here, which is exactly the physics of whether n equal 2 is large or small. Okay, so this is the plot. First of all, I obtained 2 quantities, chi, the coefficient of theta squared, and B2, which is the coefficient of theta 4. Okay, so let's take the chi topological susceptibility. Okay, so measured into string tension, and then this is the plot of 1 over n squared, 1 over n squared. So this is n equal to our result, and for this quantity, there are several other results. Actually, there are a lot of error bars and things differ a little bit, but it's true that as a tendency that it seems to be relatively large. So compare with other points. So this is n equals 3, n equals 4, n equals 5, etc. And people are interested in Lagrangian scaling. So several groups have studied this Lagrangian scaling, and indeed, in the Lagrangian limit, it seems to fit well with this linear in 1 over n squared. So which is the expected Lagrangian scaling. Okay, so, but then there seems to be begin to deviate at n equal 2. Well, of course, this is n equals 3, n equal 2. There is no data point in between, no n equal 2.5. So it's limited, but you kind of see, well, the trend that it seems to be deviating. And then in fact, this is, but the point is that it's still not diverging. So you might expect a tendency to diverge at some point. And so that's actually the point where you expect that the dilute Instanton approximation might become better. In fact, for the 2D CPN model, Lucier has done similar analysis and observed the divergence of topological susceptibility. So so you expect something like this, and that's precisely the point where the CP might recover. That's a numerology I have. So that's a small indication that maybe n equal 2 is indeed large. Okay, so what about the other coefficient, B2? So this is as far as this one's concerned, our result seems to be the only result. And again, it's fitted as a function of 1 over n squared. So this is n equal 2, this black dot point. And there are other points about n equals 3, n equal 4, 5, etc. And then again, it seems to be fit well with this 1 over n squared linear law. And what's important is that there's this dotted line below. That's the point, if I remember correctly, minus 1 over 12 or so, which is the value expected by obtained by expanding cosine. Namely, that's why the discrete Instanton gas approximation works. And the point is that this n equal 2 point, although still there are a lot of error bars, it seems to be deviate a lot from this Instanton expected value. And if you're brave enough, you can try to extrapolate, and then that will match somewhere around here. So if you fit somewhere, it's like n equal 1.5 or something. I'm not sure if the precise value matters, but and which is, by the way, if it's very similar to the value where if you fit by some function, that's where the divergence might happen. So it seems that from this analysis, already, I think that n equal 2 is actually in the large n class, and the transition between CP breaking and CP breaking and not seems to happen equals to at n equal 1.5. So it's actually 1.6 seems to be pretty large as far as this purpose is concerned. So that is the part 1 of the paper. And for this analysis, we use the expansion with this theta parameter, which a lot of people have used. And so this is already a good cross-check. For example, we obtain some value, and then there's some we can cross-check. And also we became confident about the measuring the topological charge, and improved, as I said, try to improve on the method to identify the value of the topological charge by the snaring procedure. And so that's actually okay. That I could do this wasn't too surprising to me. But of course, this is just the first two coefficients in the expansion. And as I said, that already shows that CP seems to be broken. It's n equal 2 seems to be large. But of course, I'm tempted to just plot the free energy as a function of theta, right? So that would be amazing. And I keep reading the literature, and if you keep reading the literature, conclusion is that it's impossible, simply because there is a sign problem. So there are very serious experts doing this, and people measure this coefficient. That's it. But somehow we become surprised that we actually can do better. And that's a method we call the subvolume method. And yeah, that's a new method which introduced. And that is how we could plot the f of theta, free energy as a function of theta. Okay, so what is the subvolume method? So let me try to explain this in somewhat detail. So, well, I should say that essentially the same method was used for the 2D CP1 model by this paper already in 2008. So it's actually very similar. Instead of talking about FF tilde, of course, in 2 dimensions, they are talking about F. But the procedure is actually essentially the same. But so in a sense, we adapted that to 4 dimensions. But somewhat surprising, this paper is not at all appreciated, and like it got 10 citations or so. And but anyway, I think this is yeah. So we realized that the similar thing has been done in 2D. But anyway, so this is the subvolume method. So what is the subvolume method? Okay, so if you take theta equal to pi and generate a gauge field configuration, there is a sign problem, so you cannot do that. But let's see. So instead of doing that, it's subtle, admittedly, but instead of doing theta equal pi everywhere, I take a small region inside the full volume of size L. I denoted L. So the size of this full volume L to the 4th. That's the B subvolume. And inside this region, only inside this region, I change the value of the theta parameter to be pi, for example, or whatever value of the theta parameter you want. So you can think of this as something like an insertion of operator. And in a sense, this is somewhat similar to what people usually do when you evaluate the surface tension. In that case, you introduce a Wilson loop, and you introduce a Wilson loop, and then you evaluate it. But here we are not inviting Wilson loop, but things filled in the middle. And okay, then once you have this setup, you can define this subvolume version of the free energy as a function of theta, which is defined as path integral, but where Q is only the subvolume Q. In other words, the Q topological charge is defined as sum of densities, topological charge densities from each point, but we sum only over the points inside the subvolume. And then you can define it. So it's an expectation. In practice, you measure that. And if you take the cosine and you take the expectation value, you get the subvolume theta. Okay, so this is a function of the subvolume L. And the question is, okay, so it's a function of L, and what are we going to do? So what we're going to do is to fit this function by fit this function, which also depends on L, I forgot to say, as a constant term plus the subleading piece, which is 1 over L, together with all the subleading corrections. And the idea is that, okay, so this is the leading piece. That is the actual one we want to compute. And the idea is that, okay, so there is a subvolume, so there is a surface tension. So probably there are going to be some corrections coming from the surface, which would go like 1 over L. I don't actually think there are probably no 1 over L squared, but just conservatively, there is a subleading corrections. And so that's the thing. And the idea is to, ideally, we're going to set L to infinity. If you send L to infinity, this term drops out and you get this thing. And okay, but there's one subtlety, which is the type of thing you worry about in numerics all the time, which is that, okay, so it's easy to say that L to infinity, but of course, first of all, the volume is finite, so you cannot take L to infinity. It should be smaller than subvolume, the full volume. And also, it cannot be too small compared with this typical scale of the theory, which is set by this deconfinement temperature. So there is some region of this L you can take. And the question in practice is that in this allowed value of the subvolume, can you try to fit this profile well with this function 1 over L? So that's a big question. Sometimes it doesn't work actually, which is reflection. For example, if you, yeah. So that's the reflection of this, in a sense, this sign problem. So I'm not solving the sign problem, but try to just circumnavigate it. And okay, so this is just probably details which you don't matter. So there is a you did anyway. We did the simulations. And so this is how it looks in practice. So I want to take L to infinity. So I want to go all the way to the left. And theta equals pi over 2. In this case, it's relatively simple. It's just this thing. So it's 1 over L. So we're going to fit with the linear function. And it seems to be fitting well with the linear functions. And at some point, when you send L to very zero, close to 0, then you're going to get the sign problem, etc. So it becomes worse. So we are going to do a very tricky stuff. That okay, so this is exactly the region I want to study, but it's hard to do that because of the sign problem. But even before coming a little bit away from that, sometimes you already see the, this linear behavior in 1 over L, and then you can take that and then try to extrapolate all the way to L equals infinity towards this region L, towards the left. And so for theta equal, this is theta equal pi over 2. Theta equal pi is not too bad. There is some error bars depending on how you fit. We tentatively put some systematic error. And for theta equals 3 pi over 2, the error is actually pretty large. So this is probably borderline and then probably no longer trustable, this thing. So that's the type of analysis we do. And this is the one of the results. So the one of the results is the Horos. So here is the above the confinement transition temperature. And that's the point where discrete instanton approximation becomes viable. And at this point, you expect something like a cosine function, or in other words, you expect some periodic 2 pi periodic function as a function of theta. And okay, so this is the plot. This is the well, in this case, you can actually just measure it with the full volume. There's not much of a sign problem. And then we try various different things, and depending on how you do, there's actually relatively large systematic error. If you use the subvolume method, but the point is that you create whatever you do, there's a clear trend that this seems to go start decreasing already at theta equal pi, and it's not too bad compared with this thing. And but this blue line is the expected cosine behavior. And you also check that, for example, you can take you look at the behavior and you theta equal to 0 and the coefficient of theta squared, topological susceptibility, and then try to compare with what other people computed. Etc. So there are some cross checks you can do. So here, but the point here is that there's a okay, it's not perfect, but at least you begin to see the tendency to go back, and there is a 2 pi periodicity, which is the expected behavior. Yeah, so it's certainly above the transition temperature, and it's actually already okay at 1.2, for example. We did a similar analysis for 1.6 times the critical temperature, but it's very similar. So in fact, the trend was so similar, so we didn't get that much of a configuration. So yeah, I mean, if necessary, we can certainly improve the systematics. Okay, so this is the expected behavior above the critical temperature where things deconfine. Okay, so what is the main result? So this is the main result for t equals 0. In a sense, this plot is the main result for the whole talk. So this is the free energy. I was previously writing capital F, but it's the same thing as a function of theta. It's a free energy per volume. So it starts with theta equals 0, it's 0. So that's normalization. And then there is going to increase. So so if you take the full volume thing, so and you studying the region around theta equals 0, you can just study it without using the subvolume trick, etc. And it's the data points are given here with this block boxes. And you can already fit that with a square function, and then that the coefficient topological susceptibility you can compare with other studies. But now the point is that if you use the full volume, it becomes increasingly difficult to go beyond certain point like a pi over 2. And if you want to go pi, we have to use the subvolume method. And so there are actually three squares and triangles that almost collapse into one in this plot. So these represent different ways of how to extrapolate all the way from the finite subvolume to infinite subvolume. So that's the extrapolations, and you can do extrapolation differently, but you essentially get the same result. And the trend is very, very clear. So it's going up, even as theta equals pi, it keeps going up clearly. And so as I said, things become untrustable around theta equals pi, 3 pi over 2 or somewhere. So this shouldn't be taken too much at face value, but it seems there is a clear trend that seems to be going up. And there is no way that it can come back to theta equals 0 at theta equals 2 pi. So yeah, so that's the lesson, and that fits well with our previous result that n equal to SU2 is actually more like a large n class. So if it's a large n class, you might expect multiple branches, and each branch is not 2 pi periodic. And what this shows is that we are following one of the branches, and yeah, so you're actually missing the other branches. Oh, sorry, there is a CD happening. But yeah, so maybe it's okay. Maybe I should try to wrap up. So I think it's the end of time. But so this is the main result, and so this shows that the things is not 2 pi periodic, and the CP is broken, spontaneous broken. And if you like, you can we have also plotted the derivative too, and the derivative there is also it's very clear that derivative is known. In this plot, it's a derivative, so it's important. It's not positive. It is positive at sake of pi. It's hard to imagine that this is 0. So that's a very clear indication. To me, it's almost like a proof that well, you can debate the method for subvolume method, etc. But if you accept that, it's almost a proof that it's CP is spontaneously broken for SU2. So here's a summary. So I think at least when I started working this, I really wanted to. It was kind of my dream to find this free energy as a function of theta as a function of So this plot this function. And it looks like a simple thing, but as I told you, people have tried in the past, I don't know, 40, 50 years or so, and as far as I know, nobody has really succeeded. Well, there are some trials, but my conclusion is that we have done this for SU4, SU2 YAML theory, and we can go all the way to theta equal pi at least, and that involves improving the method for snaring, but also using the subvolume method. So this you can do with despite the sign problem, and also you can do so the physical lesson is that SU2 YAMLs is actually like a large n, and there is a spontaneous CP breaking, and this is very different from the CPN model. CPN model case where CP1 is a gapless, for example. So that shows the quantitative difference between 4D and 2D, and finally there are questions. Maybe further you can increase systematics, so you can try other theories, extract the phase diagrams, and the final tempting thing is to try to do the case with a finite chemical potential to try to explore the phase diagram. Thank you.
Thank you very much. Questions? Sure.
can you go back to the summary slide? Yeah, this one here.
Yes.
So first question is why at t equals 0 we're supposed to be harder? Your 3 ways of extrapolating match so well, and that t equals 1.2.
Ah, I see.
Why
Yeah,
is
I
it
don't.
so much better?
Yeah, let's see. I don't know. In fact, well, let's see. Well, but technically, these 3 different points. Okay, so first of all, I should explain what these 3 different points are, and the 3 different points correspond to which regions of the L. So okay, there is a subvolume method. So there is a subvolume here, and we want to extrapolate with this linear function in one of L. And the question is which value of L you take. And in practice, the value of L we can take is like a 10 to 24. 24 is the size of the whole thing, and 10 is the dynamical scale is relatively large, like a 10. So we are pushing this a little bit, but only possibility is like a 10 to 24 or so. So that leaves, I think, six data points or so. And the question is that which data point to take? Are you going to use the 20 to 22 or etc.? So that's actually the way to extrapolate, and that's kind of shown here. So this is the thing, and you want to extrapolate from here to there. So these 2 lines, for example, it's a little bit difficult to see because it's dotted, but it's the type of things you might expect. So that's the technical translation of the question is that somehow for t equals 0, this plot seems to be more linear. This is t equals 0 plot, I think, and there is a similar plot for t 1 point. It's closer to linear somehow, and why it works? Yeah. So as for your original question, I have no idea actually. So why it seems to work well in somewhat surprisingly for t equals 0, better than. Yeah, above critical temperature.
But from this plot, like at theta equals 3 pi over 2, there is a huge error bar. So
yes.
you did not plot the error bar in the other summary plot, right?
Yeah, sorry. Yeah, in fact, that's right. So in fact, right. So yeah, in fact, this picture. Yeah, in fact, sorry. In fact, this picture. Yeah, I think we here, for example, already here there is a error bar, and yeah, I think this I think we should be. Oh yeah, in fact, we are supposed to continue all the way. So in fact. Yeah, I'm not sure. Indeed, this plot, I don't know why there is no error bar. I mean, we have some other plots where error bar becomes larger and larger here. Yeah, indeed. Thank you for pointing that out. So that's the point where things become untrustable.
But just one conceptual question.
Yes.
How does the lattice know that it should follow this curve and not go to the other branch of the parabola?
Yeah, that's an extremely good question. And I think that's related to the question about the fact that we are using the gauge field configuration at theta equals generator sector equals 0. So that's actually related to the overall problem of the reweighting, etc. You were bringing up the other day, etc. So what I would expect is that if you want to see the other branch, and if you want to see the first order phase transition itself on the nodes, then you should know about the other vacuum. And for that, I think it requires to generate the gauge field configuration at different values of theta. And then you have to copy the overall problem that it's hard to generate it by reweighting. So you have to generate it on the node. And in fact, the similar question is observed by, for example, if you evaluate in the evaluation of the string tension, for example. In the string tension, okay, so people say, okay, string tension, there is a linear behavior, etc. So it grows. But you expect that, for example, if you have matter quarks, etc., you expect that the string tension, it begins to, I mean, at some point you expect that their quarks and anti-quarks are generated in a pinch off, right? So you don't actually expect the linear growth to continue forever. But in practice, people see the linear growth, and that's related to the fact that that you are not finding the other vacuum. So the situation, in my opinion, is somewhat similar to that. So this method circumnavigates this overlap problem by using only the vacuum near theta equals 0, and that's why it's useful to see the vacuum. But this branch. So for the purpose of seeing the branch, it's very useful. But if you want to see the other phase transition, the other branch, you really have to change the gauge field configuration.
Domenico?
So in fact, that's what I wanted to ask you. Can't one construct at least the gauge configuration at 2 pi, which is probably possible, and then try to go back and see how the two meet at pi?
Yeah, I think it should be possible. Yeah, indeed. So indeed, that's the same as the plotting. Yeah, indeed, that should be possible. Yeah, maybe we should try that then to see how things work. And yeah, indeed. Yeah, probably that's true. Yeah. Well, let's see. Well, at least eventually let's see. let's see, but is it really the same? Well, okay. Well, if you take this, we are inserting we take the subvolume and inserting theta equal non-zero. So we are making a small region and then changing the value of theta to 2 pi there. So at least in the intermediate steps, we are doing something different. And yeah, so physics-wise, well, yeah, in fact, I have to think. Yeah, it's not completely clear indeed. That's a very good question. So if, for example, if I said previously about gauge field configuration is true, then as long as we are starting with theta equal 0, that's the, yeah, we might get the same thing, in fact.
Maybe I'm going a bit out on a limb, but can it just be that if your curve is symmetric between theta minus theta, then it's sort of obvious that the two things have to meet, and then it's clear that there has to be a first order transformation.
Yes.
I would say.
Yeah.
I mean, what I'm trying to say, if you try to do stuff around 2 pi, and you go back, it's the same thing.
I think that's true. So there's definitely symmetry, so it goes all the way. Yeah. Yes. Yes. Yeah, that's right. And of course, you know that already know that the physics should be 2 pi periodic if you take the minimum branch. So yeah, there's already a guarantee that there should be another branch. And indeed, that's the one coming from theta equal 2 pi, as you say. So yeah, so conceptual level, I think that's not really necessary, but maybe it's good to see how it works in practice.
I have also one small question. So in these high spin theories, people study these HS lambda theories, which people you should think of as being SU lambda. So, so is there some way of maybe extrapolating between SU2 and SU1 and really working at SU1.5?
Yeah, let's see. That's a very interesting question. Yeah, I have to think. Maybe you can, yeah, include some extra ingredients and take the scaling limit and things like that. And yeah, in fact, that's a very interesting question. And because that makes it possible to identify the critical value precisely.
Exactly,
yeah. Thank you. Yes. And yeah, I mean, what we have done so far is just taking up n equal 2, n equal 3, and try to interpolate. And right, but it's really nice to have some setup like that.
Okay, in view of the time, let's thank Masahito again.